start with roughly where we left off last time, which was looking at neurotransmitters, receptors, and for that, in-class quiz we just talked about, hopefully that jogged your guys' memory on some of the important aspects of how things function. And remember, we could talk about neurotransmitters, the receptors, and all the pathways those receptors talk to as a system. And so we can talk about neurotransmission systems in which we can look at, say, the neurotransmitter, in this case acetylcholine. And remember, there's more than one receptor that can bind acetylcholine, and so you can get more than one response depending on whether that particular cells have a different type of receptor. And so here we can talk about, acetylcholine as a neurotransmitter, so we can talk about cholinergic signaling. And then in order to specify which type of receptor, you have to specify which tissue or the cells that we're talking about. So here at the neuromuscular junction, now you know that acetylcholine is causing an excitatory postsynaptic potential. But if we're talking about cholinergic signaling in cardiac muscle, okay, now what type of receptor are we looking at there that acetylcholine binds? Is it going to be a ligand-gated ion channel? No. What is the other type of receptor we talked about? Does indirect GPCR. That's almost always guaranteed to be the answer anytime I ask you guys about what other receptor or what receptor is this. If you say GPCR, you're probably right. So if you want to hazard a guess, hazard the guess of GPCR. All right. So yeah, so it's a GPCR that acetylcholine binds to in cardiac muscle. Instead of activating or causing excitatory postsynaptic potential, it does the opposite, meaning that it's causing inhibitory postsynaptic potential. Now, if it's inhibitory, it means it's less likely to cause an action potential in that target tissue, which means are we getting closer or further away from threshold? So hopefully you guys are thinking further away. So I'm working on my telepathy since you guys aren't talking to me. So I'm trying to read your minds, right? So further away. And in the neuromuscular junction, we're talking about getting closer or further away from the threshold. Closer, right? More likely to cause an action. All right, so some examples of neurotransmitters. There's dozens upon dozens of neurotransmitters and other molecules that affect neurotransmission. Do you have to know them all? Yes. No, you don't. All right? You don't have to know them all. I've got a list there towards the end, as well as in the lab and as we talk about it, of ones that you should know, especially, some that affect, important pathways. All right? So let's just kind of go down and talk about some of these. So acetylcholine. So what do we know about acetylcholine? What does it do? So where is it important? So what structure? Yeah, skeletal muscles, right? And also cardiac and smooth muscle, right? It's important as an excitatory neurotransmitter to initiate skeletal muscle contraction. Okay? All right, so dopamine, maybe, does anybody remember looking at dopamine? It's all right if you don't. So dopamine is kind of a feel-good neurotransmitter, also involved with reward. So feeling good about getting a reward is also involves dopamine. There's other things that these neurotransmitters are involved with. We're not going to talk about them all. It's very complicated. All right, what about serotonin? So serotonin. Yeah, so it's involved with mood stabilizer. So it minimizes the huge swings that, we can have in mood. So it acts as a mood stabilizer. So norepinephrine. So we talked a little bit about epinephrine and norepinephrine. Norepinephrine is involved in a response that sometimes is referred to as the fight or flight response. So if you're out hiking, you see a bear, okay, right? Fight or flight. So what ends up happening in a fight or flight response? When you get startled, what happens to your heart rate? It goes up, right? So one of the things is that it's going to increase heart rate, and it increases the contraction force of the heart too. So those two things are important. When you get to cardiovascular section, we're going to talk about even more things that, norepinephrine does. So it's going to be important when you talk about the autonomic nervous system as part of what we call the sympathetic nervous system, or sympathetic division of the nervous system. All right, so next one's GABA. So that is a major inhibitory neurotransmitter in the central nervous system, in the brain. GABA. We're going to talk about so if it's inhibitory, then it means that are we getting closer or further away from that threshold? Further away, so that's what it's doing. And so, yeah, it does kind of diminish, a lot of aspects of the brain, including, we'll talk a little bit about it in just a second in drugs, but, including, I guess, your interaction with your surroundings, so you diminish, the ability to process that information, the memory and so forth, so it's kind of acting like the brakes. Okay. All right, the other one is glutamate, and this is the main excitatory neurotransmitter in the brain. So GABA and glutamate are kind of opposite sides of the same thing. So GABA puts the brakes on, glutamate is going to be the accelerator. All right. So here, it's an excitatory neurotransmitter. Are we getting closer or further away from threshold? Closer, exactly. All right. So GABA and glutamate, all right, are taking that membrane potential, right, either closer or further away from threshold. Okay. So major inhibitory, major excitatory neurotransmitters in the brain. Substance P is one of the neurotransmitters, substances out there that is going to be relaying information with respect to pain. Substance P. So, pain. On the opposite side, we have molecules that are called endorphins, a class of molecules called endorphins, which inhibit substance P signaling. So they inhibit pain sensation, propagation of that signaling to our brain. Okay. Yeah, we call it analgesia. Right? So analgesic. Right. So it turns out endorphins, dynorphins, and epinephrines, these are the major ones that target opioid receptors. So opioids, a lot of them are used to diminish pain or treat pain. Right? They do so by inhibiting the pain being propagated, the pain sensation being propagated to our central nervous system. So substance P does a lot of that initiation of that pain system. There's other molecules out there that do that. All right? Okay, so next one, adenosine. All right, so this one is the one I think maybe you guys were thinking about in the back. It's involved with sleep-wake cycle. It's also involved with the cardiovascular system, the circulatory system. And it is also going to be the target of caffeine. So caffeine antagonizes the effects of adenosine. So adenosine, caffeine will help with staying awake, focus, but it also has cardiovascular effects. Caffeine does a lot of things, but one of the major targets is going to be this adenosine signaling pathway. All right? And the last one are endocannabinoids. So anyone can take a guess as to what responses are of endocannabinoids bind to endocannabinoid receptors? Same as THC, basically, right? So here they're involved with, not surprisingly, appetite. Also involved with, inhibiting nausea. And also a little bit with memory. A little bit with memory. All right? And so I've got a few images here. Right? So go through and see if you can match the images with some of these neurotransmitters. Okay? So when you guys get a chance, go through the images, see if you can match them with the neurotransmitters. All right? So here, there's a lot of things neurotransmitters do, and we're just highlighting a few of them. Okay. So now we get into what I think is the fun part. What happens when we have molecules that are interfering with neurotransmission? So drugs, toxins, poisons, and so forth. All right? So one of these, a few of these, for those that had me for 231, we've ran into already. So remember, all right, that in order for a neurotransmitter to be released from the presynaptic vesicle, right, you have to have calcium coming in, which is going to cause that vesicle to dock with the cell membrane using snare proteins. So remember I told you that I was introducing snare proteins because we're going to be talking about them as targets for certain types of poisons, toxins. And so here what ends up happening is those snare proteins kind of come together when calcium's present, and they help with merging of that vesicle with the plasma membrane and creating an opening for the neurotransmitter to be released. So do we get neurotransmitter release if we disrupt snare proteins? What do you guys think? So if we disrupt snare proteins, we take them out, we don't get neurotransmitter release, right? So one of these toxins that does that is botulinum toxin. So what it ends up doing is that botulinum toxin degrades snare proteins, and if it degrades snare proteins, then we're not going to get that vesicle docking with the membrane to release neurotransmitters. So if this happens at the neuromuscular junction, if it's happening at the neuromuscular junction, what neurotransmitter gets released from the motor neuron? So what neurotransmitter is that? Acetylcholine, right? So if we have botulinum toxin, what happens to the amount of acetylcholine being released from that motor neuron? Is it going up or down? Going down. So what does that mean with respect to the skeletal muscle? Is it staying contracted, or is it relaxing? Relaxing, right? Because in order to get contractions, we have to have acetylcholine bind to acetylcholine receptor, but we're not allowing acetylcholine to be released with botulinum toxin on board, right? So here, when we have muscles that stay relaxed, we call that flaccid paralysis. Flaccid paralysis. Okay? So one of the things that you're going to want to be able to do mentally is talk about, all right, if we have this drug, or this poison, or this toxin, right? What is it affecting? What part of neurotransmission is it affecting? Okay. What is it doing for the amount of neurotransmitter in the synapse? And depending upon what that effect is on the neurotransmitter, what consequence is that going to have on the tissue that has that receptor? Right? So those are the general steps, sequence of thinking that you want to get into. Okay, so another toxin here is tetanus toxin. I have to introduce a little bit more about how the neurotransmission operates at the neuromuscular junction and talk about how this toxin works. So you guys are familiar with the motor neuron releases acetylcholine, which causes the skeletal muscle to contract, right? Everybody comfortable with that? Okay? So it turns out that this is the motor neuron. Here's our skeletal muscle, let's say. There's another neuron that releases an inhibitory neurotransmitter. Okay, if it's inhibitory, is it making it more likely or less likely for an action potential to occur? Less likely, right? So this inhibitory neurotransmitter, these Gs, stand for glycine, okay, which is making it less likely for action potentials to be propagated down or be initiated in the motor neuron. Okay, so it's kind of like putting the brakes on the motor neuron. So if we're putting the brakes on the motor neuron, what are we doing to the amount of acetylcholine being released? Are we increasing or decreasing? Should be decreasing, right? Right. So here in a normal situation, this neuron is making sure that not too much acetylcholine gets released, just the right amount gets released. Everybody with me on that? Okay. That's how it works. This tetanus toxin, what it does is it takes out the brakes. So if we take out the brakes here, what is that going to do to the amount of acetylcholine released by the motor neurons? Is that going to go up or down? It should go up, right? So think about a car that's driving along. If you take out the brakes, it's probably more likely to go faster, right? Not slow down. Okay? That's exactly how tetanus toxin works. It targets this kind of inhibitory neuron, which means that we're going to get a lot more acetylcholine release. And then what is that going to do to skeletal muscle? It's going to stay more likely contracted or relaxed. Contracted, right? And so staying more contracted, that type of paralysis is called spastic paralysis. So we just talked about two types of paralysis, right? Flaccid and spastic. In both cases, the diaphragm, which helps us breathe, is a skeletal muscle. And it needs to rhythmically go through a series of contraction and relaxation. So if we are stuck in spastic paralysis, are we going to have problems breathing? Yes. If we're stuck in flaccid paralysis, are we going to have problems breathing? Yes. And that's the major problem with this type of paralysis, respiratory failure. Okay. So, like I said, here drugs, toxins impact a lot of aspects of neuronal communication. A lot of them can be psychoactive, but not all of them have to be. They can be influencing the action potential, which means that they're influencing neurotransmitter release, and they're affecting axon terminal events. So the basic series of steps that you want to go through mentally to try to figure out what the consequences are of a drug or a toxin or a poison here, is to think about what is it affecting in the neurotransmission system? How's that affecting the neurotransmitter binding? And then what consequences is that having on the effector itself? Okay? There's a few terms I need to introduce here. So the term agonist means that it binds and stimulates the receptor. Okay? So it mimics the actions of the ligand. So if I had an agonist of acetylcholine, right? An agonist of the acetylcholine receptor, it mimics the actions of acetylcholine. So it binds to that receptor and causes the same effect on that part of the tissue as acetylcholine. The other type of molecule, small molecule here, is one called an antagonist, and it acts kind of like someone who parks in someone's designated parking spot. It blocks the ability of the normal ligand, the normal neurotransmitter, to dock with the neurotransmitter receptor. So if we had a acetylcholine receptor antagonist, it blocks the ability of acetylcholine to bind to the acetylcholine receptor. And if we're talking about at the neuromuscular junction, what type of paralysis would you expect from an acetylcholine receptor antagonist? Flaccid, right? So how did you do that mental gymnastics? Well, you know that acetylcholine binding to the acetylcholine receptor causes skeletal muscle contraction. So here, if we have something blocking that, then that signal for contraction is not getting through. Right? And so here we're blocking that signal, which means that the muscle isn't receiving the contraction signal. So it stays relaxed. Everybody follow me on that? So agonist is mimicking the actions of the ligand, the chemical, right? And the antagonist is blocking. Everybody with me on that so far? Okay, good. All right, so why don't we do this? Why don't we take a 5-minute break? Everybody back. Okay, so like I said, these are kind of things that you should be asking yourself to try to figure out what the consequences or the impact is going to be on a target tissue and effector. Okay, so where in the normal flow of those sequence of events does this disruption occur? Is the result that cause more or less neurotransmitter? And then what's that effect, the consequence of having more or less neurotransmitter? What does that do? Okay. All right. And so here, serotonin's kind of involved with mood and emotion. GABA is the major neurotransmitter for slowing things down in the brain. So inhibitory dopamine is involved, with a variety of things, including euphoria and bliss. And also a reward pathway, norepinephrine. Epinephrine is involved with a sympathetic response, and that includes what we talked about, the impact on the heart, right? Increasing contraction strength, and then also heart rate, the beating frequency. Okay, so let's talk about a few of these guys. So serin inhibits acetylcholinesterase. So if it inhibits acetylcholinesterase, what impact is this going to have at the neuromuscular junction? So let's start off with what's going to happen to the amount of acetylcholine at the neuromuscular junction. So if we inhibit, so what does acetylcholinesterase do? So it's breaking down acetylcholine. So if we have an inhibitor of the thing that breaks down acetylcholine, what is that going to do to acetylcholine? Go up, right? So the acetylcholinesterase is breaking things down, and we're taking that out. Which means that now we don't have that enzyme to take out acetylcholine, so it's going to be elevated. The amounts of acetylcholine are elevated. What impact is that going to have on muscle? Skeletal muscle. So I heard the word spastic paralysis. Everybody agree with that? Does that make sense to folks? So hopefully you're convincing yourself that acetylcholinesterase inhibitor, like serin gas, right, would cause spastic paralysis. So everybody able to follow that sequence of events, how we got to the conclusion that this would cause spastic paralysis? Because if not, please let me know, and we'll break it down again. So the whole point is we're taking out what is breaking down acetylcholine, right? So here, if we have acetylcholinesterase, that's removing acetylcholine. If we take out or remove what's supposed to be removing acetylcholine, then we elevate acetylcholine levels, which means that we're stimulating skeletal muscle to contract more frequently. All right, so some other ways to modify that, synaptic transmission is to block the reuptake. So maybe you guys have heard of reuptake inhibitors. One type is called selective serotonin reuptake inhibitors, or SSRIs. So here, what is that going to do to the amount of serotonin in the synapse? So if we block reuptake, we inhibit it. Is that going to go up or down? It should go up, right? So we're inhibiting the amount of serotonin that can be taken back up, which means that it's going to elevate that. And then here, that neurotransmitter is involved, like a lot of neurotransmitters, in a wide variety of locations. And that includes the limbic system in the brain. The limbic system, we'll talk about more. It's involved with emotional memory a lot of times. So if you ever walked into a room and there was a kind of a smell that you didn't like, you kind of have that visceral response, that kind of quick reflex. That's part of the limbic system being triggered. Is that this visceral quick reflex is involved the limbic system. Right? So here, the limbic system, for our purposes, as at this point in the course, is the center of our emotion. And so here, it's going to be these SSRIs are important, with treating depression. And they need to be monitored so that the levels are just right, because if you have an imbalance in neurotransmitters, it can cause all sorts of problems, right? And cause other issues worse than the ones that you're looking at. Okay, yeah, go ahead. Mm-hmm. Yeah. And there's other ways that it can be removed by other cells in there. But yeah, and that could be problematic, which is why you need to monitor kind of people's, dispositions and moods, with this, because there can be other problems if it gets too high. Okay. So here, this is just kind of a cartoon of what we're talking about. So if this is the neurotransmitter serotonin, it's our presynaptic neuron. Here's our postsynaptic neuron. All right. And so here's our reuptake, so our transporter. If we have a SSRI, okay, that blocks it, then the neurotransmitters aren't, in this case, serotonin, aren't going to be able to be taken back up. Okay, that's what we're talking about. Okay, so another drug, cocaine. So cocaine inhibiting the reuptake of dopamine is also going to impact the reuptake of epinephrine, norepinephrine. Right? So here, this is part of the reward and pleasure center of the brain, creating euphoria. And so dopamine release and the reward and motion centers, are elevated. And so blockage of norepinephrine uptake can have heart impact, though. So remember, what does epinephrine, norepinephrine do to the heart? So what about the heart rate? What happens to that? It goes up, right? Contraction strength also increases, right? So one of the side effects, of this is that you increase cardiovascular, could have cardiovascular impact. So in an effort to maintain euphoria, individuals that are taking cocaine are impacting their cardiovascular health. Okay, so those were some reuptake inhibitors. So, antagonists, one is called alpha bungarotoxin, acts as an antagonist for the acetylcholine receptors at the neuromuscular junction. So what's the effect going to be? So if it's acting as an antagonist to the acetylcholine receptor, what effect is that going to have on skeletal muscle? So here in flaccid, not going to be able to contract. So that's basically the definition of flaccid paralysis. Not going to be able to contract. Hopefully people are able to follow their way through this. So if we have an antagonist, it's blocking that receptor, meaning that the normal neurotransmitter or ligand, that chemical, can't bind to it. Meaning that anything downstream or anything that receptor is going to be doing to the effector can't happen. Or at least it's reduced. All right. So some agonists here. So here, GABA, remember, is a major inhibitory neurotransmitter in the brain. And there's a few molecules that have similar effects, so they act kind of like GABA mimics, right? Agonists. So alcohol, PCBs, benzodiazepine act somewhat as agonists of GABA. And so does that mean that we are pushing down the brake pedal or the accelerator? So if they're mimicking the effects of GABA, and GABA is an inhibitory neurotransmitter, the brakes, exactly, right? So it's mimicking pressing down on the brakes. In some cases, some of these mimics, these agonists, are stronger and push down on the brakes even more than GABA normally does. So inhibiting those pathways that GABA usually inhibits, it inhibits them even more. So, Valium, for instance, also rohypnol, rupees, date rape drug, affects this pathway. Right? And it's putting the brakes on a lot of these pathways, inhibiting memory formation, and other aspects of this. Right? So motion, fear, memory is all kind of reduced here in response to stimulation with GABA pathway. Go ahead, Tyler. Mm-hmm. It's a good question. It's a little bit more complicated than that. They kind of fight it out for binding to the receptor. And kind of the question becomes which one has stronger affinity for the receptor, right? Is one of the things that influences that conversation, right? And so, yes, you can counter agonists with antagonists, and you can do the opposite. So they kind of duel it out for binding to the receptor. And so that's one of the ways that we'll talk about the treatment of, say, opioids. You're absolutely correct. Okay, so there's also some drugs that can have mixed effects. So methamphetamines, they can stimulate dopamine release from the axon terminal and inhibit reuptake. And so this results in elevated amounts of these neurotransmitters. So if we have elevated amounts of these neurotransmitters, that means that those cells that have the neurotransmitter receptor for them, for those neurotransmitters, are being overstimulated, right? In an effort to try to minimize that overstimulation, those cells try to reduce the amount of receptors they have on their surface. So this is called downregulation. Okay? So what do I mean by that? Well, let's say that we have 100 receptors on a postsynaptic cell. Okay? And normally only 50 of them are bound in a situation where we don't have, say, methamphetamines on board. Okay? Now, what if we put methamphetamines on board and we now increase the number of receptors on a postsynaptic cell instead of having 50 out of 100 binding to, neurotransmitter? Let's say all of them do. Okay? Let's say 100 out of 100 do. So now we've got this huge response in the postsynaptic cell. So what does that cell do to try to minimize that huge response? Well, it tries to reduce the number of receptors. So if we reduce the number of receptors, okay, say we go from 100 down to, 25 maybe, to reduce, right, that response, okay? Now we only have 25 receptors on that postsynaptic cell where we started out with 100, okay? What if we take methamphetamines away? Take them away. Now that neurotransmitter, it's only at the maximum is able to bind to 25 receptors, right? So if that neurotransmitter is important in, say, making you feel okay, being able to cope with situations, if there's not enough of that ability, you feel kind of miserable, right? So what do you end up doing? You go back to try to make yourself feel good, which is go back on the drug, okay, in order to stimulate more of those receptors. So it's a downward spiral that happens, right? Those receptors get downregulated, people go off of them, off the drug, and now there's not as many receptors to get stimulated, right? when they're off the drug, and so they don't feel as good, so they go back on the drug to feel better. Okay? And this is one of the spiral problems that happens a lot in drug abuse, and it has to do with its downregulation of receptors. Now, we'll also talk about this when we talk about beta blockers in the cardiovascular system. So this whole idea we're going to see come up over and over again. So, quick question. Yeah. Not necessarily. Not necessarily. Yes, it's a little bit more with the addiction cycle. Yes, absolutely. Yes. Yes, that too. Yep. Yeah, being able to tolerate. Because now you've lowered, the number of receptors. And so, yeah, absolutely. Mm-hmm. They can. They can. And it's really important because while they're coming back, though, they're feeling miserable. So this is the recovery phase. Yeah. And sometimes it can take a long time for that. Okay. So, intense dopamine release, especially in the reward pathways of the brain. All right. Fixation, obsession, reduced appetite, not needing to sleep, increasing doses of exposure. All of these, are going to be parts of the dopamine pathway. Right. Okay. So I want to make sure to get through this because opioid addiction is such a problem here in the country. All right. So there's a good chance that either, you know somebody or you know somebody who knows somebody that's affected by opioid abuse. I can tell you from my personal experience that I know someone in my family who's affected by opioid abuse. So there's a good chance that you guys are seeing this. So looking at the rise of, opioid deaths, opioid-related deaths. Right? So here we have heroin, here we have commonly prescribed opioids, and then synthetic opioids, and then all opioids. Okay? So you can see that it's a kind of a exponential rise. So it's a huge crisis. So it's not just a linear increase in the problem, it's an exponential increase in the problem. And just yesterday, an article came out showing that odds of dying from accidental opioid overdose in the U.S. surpasses those of dying in a car accident. Pretty shocking, right? So it's a major crisis here in the U.S. It not only affects those that are opioid addicted, but also those, that are pregnant. So here, infants that are born to mothers who are addicted to opioids go through withdrawal. Right? And that is increasing as well. There's a real tragedy. Ability to be addicted is really high with opioids. So if we take a look at days of supply of opioids prescribed. So notice here that once you hit to about the 7 to 10 day mark, after that it goes up sharply. Okay? So if you're prescribed, 10 days worth of opioids, a year later, you're about 20% likely to still be using opioids. 3 years, you're about 15% likely to still be using opioids. So here, the amount of opioids prescribed strongly influences the ability of people to be addicted, and it happens in a short amount of time. So one of the things is, in addition to opioids interfering with pain, so being able to manage pain, stimulation of opioid receptors, which there's 3 types. You don't have to memorize them. I just want to point them out for people. Okay? So the mu, delta, and kappa. Most of the opioids target the mu receptor, which is involved with euphoria and stress coping. So in addition to blunting pain, it's also stimulating euphoria and stress coping, right? And so you can see how people would become addicted to that, right? So these opioids don't just influence pain management, but they're influencing other aspects. of our body, our mood. Strength of opioids. This is mind-boggling. So if we take a look at morphine as being the normalized amount, look how much more potent fentanyl is. Strongly potent, more potent. There's one synthetic opioids that are even more potent than this. So they had to resize the scale for fentanyl down to this. Right? And now look at some of these other synthetics. Carfentanil is used to tranquilize elephants. Compared to fentanyl, it's hugely potent. So we're talking about kind of just granules of this stuff. So some of those synthetics out there, when we're talking about overdosing, this is one of the problems, is that these synthetics are so potent that people don't realize, and sometimes they don't know they're in their opioids that they are taking illegally, right? So if you don't know how much fentanyl or some of these other synthetics are in what you're taking, you could overdose quite quickly. Just take a look how more potent they are. It's pretty crazy, right? Yeah, sorry, go ahead. You mean the y-axis? It's potent. It's basically how potent they are, right? So the minimal dose and maximum dose, right? So we're talking about how they can affect the opioid system. So what they're doing is they're taking opioids and they're figuring out how strongly they're binding to the receptor. And so here, the more strongly they bind to the receptor, the longer they're going to stay there on the receptor stimulating. That's the major way in which they're looking at it. The other way they look at them is they look at the pathways that are generated from binding to the receptor. Okay. And so they're saying, okay, what's the minimum dose you need for pain management? What's the maximum dose that someone can tolerate? And so those are the two major ways that are looking at it. Finding affinity is the major one. Yeah. So this is a fold increase. So it's normalized, like I said, for morphine as being 1. Yes. Thank you. So it's fold strength. Yeah. Okay. So this is getting to overdoses. How to treat overdoses. Some things that you use to treat opioid overdoses. So here, all the pluses are agonists, all the minuses are antagonists. And so you can see that here we have a lot of these agonists. So one of them is methadone. So it's not as much of an agonist as some of the other, opioids out there. But it's not a complete blocker. So it does stimulate the opioid receptor a little bit. So we call that partial agonist. Now, another one is buprenorphine. It's also used. One is severely underused is naloxone, which is an antagonist. So this also goes by the brand name Narcan for treatment of overdose. Okay. All right. So I just want to finish this up real quick. You don't have to know all the things that we talked about. I've highlighted the ones that you do need to know. So you do need to know that acetylcholine, glutamate, and substance P are excitatory, and that acetylcholine, GABA, glycine, and adenosine are inhibitory. You do need to know the neurotransmitter mechanism, direct or indirect. Acetylcholine can be direct or indirect, and then norepinephrine is going to be primarily indirect. And these are the neurotransmitter and drugs that you need to know. There's a table worksheet also on Blackboard with these exact same drugs and neurotransmitters. So you don't have to know all that we talked about. These are the ones to focus on. All right? Okay, I wanted to make sure to get through that. All right.